classes on fundamentals of electrical circuits, wherein we focus on power measurements. This is a very important topic, and we are now in session 3. So far, we have been looking at basics of power measurement as also power measurement that's possible in single-phase AC circuits. We are moving on to three-phase AC circuits in the coming session, but in this session, we will consolidate, or actually it may be called as divide the topics in power itself and consolidate our knowledge. Okay, one power portion is active power, another is reactive power, and what connects between them, which is the power factor. So in this session, we'll be discussing mostly problems revolving around the concepts associated with the differences between the active and the reactive power and how it can be made available, that is reactive power, such that power factors improve. Okay, so most of the problems are of that nature, and we have to read through the problems. There aren't many figures, so please let us focus on what is being conveyed here. For instance, in the first problem, a fixed capacitor of reactance minus J 0.02 ohms. It's connected in parallel. I suppose the figure comes to your mind, though it's drawn here. If you're writing the gate context, it's good to have a visual understanding as you read through the problems. Okay, is connected in parallel across a series combination of a fixed inductor of reactance J 0.01. Okay, so there's an inductor and a variable resistance R. Okay, so I suppose the picture is now clear. There is the reactance of minus J 0.02. So a capacitor should come to your mind, because only capacitor has negative reactance. Okay, and then parallel to it, it has a resistor inductor combination where the resistor alone varies. Okay, as R is varied from 0 to infinity, the locus diagram of the admittance of this LCR circuit will be. Okay, so please focus on the admittance. So let's think in terms of admittance. So the first circuit with a negative reactance of minus J 0.02 becomes plus J50. Okay, and it is held parallel to a resistor inductor combination, which is the same as equal to R plus J 0.01. But of course, when it becomes admittance, it becomes 1 by, okay, not 1 by R plus 1 by J 0.01, the combination. So it's 1 by R plus J 0.01. These things are elementary, but it's useful. Okay, why do we put them in this manner? Because now this is the circuit diagram that has come about as a result of this understanding is that there is a J50, okay, in parallel with another admittance as given by 1 by R plus J 0.01. Okay, and now we allow R to vary. Okay, so let's let R, of course, the first case is when R is equal to 0. When R is equal to 0, it's clear that we are having J50 in parallel with, okay, of course, admittance J50 in parallel with J100. Okay, of course, it becomes minus J100. Okay, so in total, it is the admittance is equal to minus J50. Okay, so minus J50 in the diagram, of course, it is a negative, and it is imaginary. It's not real. Okay, now moving on to the other extreme when R is equal to infinity. When R is equal to infinity, it's clear that you have what is called as R equal to infinity on the denominator, which makes this path 0. Okay, what do you mean by which makes the admittance 0 of the path parallel to J50? It means that the impedance is infinite, or there is an open circuit. So there is only one path there, and that is given by J50. And so we have what is called as the locus as going from minus J50 to plus J50. Okay, meanwhile, as R changes, the angle continues to change, and so we have a circular kind of proceeding, especially when we come to a case wherein we are having an equation of, when we are having J50 being equated to to a situation wherein we are having a real component. Okay, so that's what is, when you equate them, when you put them together, there's only a real component left, and that is what is happening at when this locus crosses the real axis. Okay, so answer A is correct. We are having a semi diameter. The locus is a semi circle of diameter J100 and with its center at 0. Okay, so it's obvious. I hope the understanding is mostly that we can think in terms of admittances, and when we think in terms of admittances, we should not forget that there is an impedance also involved. Okay, so coming to problem number 2, a 240 volt single phase. So 240 is line to line. Okay, when you though it's single phase. Okay, so that should be ingrained in our mind. Is connected to a load with an impedance of 10 angle 60. Okay, so it has a real component, it has a resistive component as also a reactive component. Okay, a capacitor is connected in parallel with the load. Obviously, when you are talking about 10 angle 60, it's an inductive reactance, and so a capacitance is connected in parallel with the load. If the capacitor supplies 1250 watt, okay, so the capacitor is a pure capacitor, it supplies only watt. Okay, the real power supplied by the source. So the real power is being supplied by the source, and some of the reactive power is perhaps handled by the capacitor, or perhaps it's pumping back watt. But our understanding or our requirement is only to find out the active power involved. Okay, so this is the distinction that we have to make. So what's the active power involved? We have 240 volts. It is RMS value, and it is line to neutral. Okay, so we have 240 because it's single phase, 240 volts, and then there is an impedance of 10 ohms. So 240 divided by 10 is 24 amps, and then there is a power factor involved, which is cos 60. So put them all together, it is 2880. Okay, so only when we are going for three-phase circuits, we have to think about line to line. Okay, so this is all RMS value, that's all. Okay, so moving on to problem number 3. Again, the pictures, but what is given is that the input voltage given to a converter is V1 is equal to 100 root 2 sine 100 pi t. So omega is 100 pi volts. Okay, and the current drawn by the converter, because it's a converter, it has several harmonic components. Like for instance, the fundamental is 10 root 2 sine 100 pi t minus pi by 3. So there's an angle of lag. The next component of the current harmonic component is the amplitude is low as expected, but it gives rise to a 5 root 2 amplitude sine 300 pi t. So it's a third harmonic. Okay, plus pi by 4. Okay, there is an angle of lead. Okay, the next component is 2 root 2 sine 500 fifth harmonic pi t minus pi by 6. So the fact that harmonics are there when you are using a converter for drawing current is clear. Okay, so now what is asked is the input power factor of the converter. This is the problem that we have to make a distinction with respect to the ordinary true power factor. Okay, so the true power factor is obtained by getting the power factor from with respect to the fundamentals and then multiplying it by the distortion factor. So what is the distortion factor? Distortion factor is given by taking the fundamental RMS value and then the total RMS value. The fundamental RMS value obviously of the current is 10 root 2 by root 2 because the maximum value is given, and the total RMS is given by 10 root 2 square plus 5 root 2 square plus 2 root 2 square and then taking the square root. Okay, so we see that it's equal to 129 square root of 129. Okay, so the power factor, as we know, which is from the fundamental, which is the same as equal to cos of the angular difference between the voltage and current is pi by 3 or 60 degrees. So cos 60 is 0.5 multiplied by 10 by near around 11. So it must be a little smaller than 0.5. So if you look from for the answers, 0.31 is too small, 0.5 is not true, 0.77 is too large. So B is equal to 0.44 seems to be appropriate. Of course, we can take the numerical value and we'll see that we arrive at the correct answer. Okay, there's a B part of the problem. It says that the active power drawn by the converter. So active power, only the voltage and currents which are of the same frequency give draw power. The rest is all heat. Okay, so we have this is the active power. Okay, so the active power is given by 100 root 2, which is the voltage, divided by root 2, such that we get the RMS value multiplied by 10 root 2 by root 2. So 100 into 10,000, and then cosine of the angle between them, which is 60 degrees or pi by 3. So we have the answer is equal to 500 watts. Okay, so this is a very simple problem, but then we should not make mistakes. Okay, so moving on to the next problem. So here we have a circuit. So let's see what the circuit tells us. There's an input voltage V1, it's a single phase circuit, and across the resistor we have voltage V2, and then across the combination of resistor and inductor, which is actually the load, we have a voltage as given as measured by V3. Okay, and what is given is, of course, we are given certain answers, and just above that we see that the power factor of the load is okay. So only the load needs to be considered, or R is not taken into consideration, only RL and X. Okay, so the circuits shown, the 3 voltmeter readings, V1 is equal to 220 volt, V2 is equal to 122 volt, and V3 is equal to 136. A rough diagram has been drawn just to drive in a particular concept. Okay, so we have 136, 122 and 220 making up a triangle. Okay, so 136, based on the load, it has a component which is in phase with 122, or the voltage across the resistor, and there's another component which is at 90 degrees with this. Okay, so we have 2 components. Okay, so for just as a method that you can experiment with, I have just chosen power factor is equal to 0.5, just that such that the triangles become a little more friendly and familiar to you. Okay, for argument's sake, if we take power factor as equal to 0.5, why? Because it is somewhere midway between the different power factor answers given, and moreover we would like to experiment with the triangle. Okay, so if power factor is equal to 0.5, okay, then we have 220 as a combination of 122 plus the component of 136 on the horizontal axis, which is equal to which is the same as equal to 68. So 122 plus 68 gives you 190, and then we have the other component on the vertically, which is equal to 118. So when you square them and add them, you see that it is very large. Why is it so? Because we have chosen a larger power factor. Okay, if the power factor was smaller, it would mean a bigger angle. Okay, a bigger angle, and so we would have, so it would have been, that is, it would have been equal to 220. Okay, so we reject 0.5. We reject 0.55 and 0.6 because they are larger power factors, which means smaller angles. But of course 0.45 is smaller, but of course you can also use the conventional method to calculate. This is just for speeding up the understanding, as also the method of doing the problem, wherein we have chosen a particular power factor which is easy to assess, because we know that that when you are having a power factor equal to 0.5, then it means that you are having an angle as large as 60 degrees. So sine 60 is going to be root 3 by 2, and you can use that. Okay, and you can see that as the angle becomes larger, the power factor continues to reduce. So we require what may be called as a larger angle here. And that's the reason why rather than 0.5 we go for the lesser value, which is 0.45. Okay, and thereafter the problem proceeds to say that if RL is equal to 5 ohms, the approximate power consumption in the load. Okay, so we have already accepted 0.45 as the power factor, a speedy way of doing the problem, and then we see that the power consumed by the load will be given by the voltage across it, that is 136. Okay, and multiplied by what is applicable across the resistor, so it's 0.45. so now we get the voltage across the resistor, then square it and divide it by the resistance value 5, that will give you the power consumed, V square by R. But of course we have since they happen to be in series, we have divided the voltage such that a portion of it comes across R. Okay, so that's all. Okay, yeah, moving on to the next problem. Here we have a 230 volt RMS source supplies power to 2 loads connected in parallel. So both the loads are drawing power, okay, and they are connected in parallel. The first load draws 10 kilowatt at 0.8 power factor leading, and the second one draws 10 kVA at 0.8 lagging power factor. Okay, the complex power delivered by the source. Okay, so here we are having a mixture of all sorts of information from which we are going to glean out what is important. Okay, first draws 10 kilowatt. So 10 kilowatt is the active power, okay, at 0.8 leading power factor. What does it mean? That is 10 divided by 0.8. Okay, when you are saying that the power factor is 0.8, it means that sin phi is equal to 0.6. Okay, so 10 divided by 0.8 multiplied by 0.6 is going to give you 7.5, and it is leading. So I have drawn the picture downward. Okay, you can also consider it as negative. Okay, moving on to the next machine, which is drawing 10 kVA. Okay, so 10 kVA, which has a lagging power factor, as given by 0.8. So 10 into 0.8 tells us that we are having 8 kilowatt of active power being drawn by the second machine, and it has a reactive requirement of 10 into 0.6, because 0.8 and 0.6 always come together. Okay, so we are having 6, but of course since it's lagging power factor, it is considered to be positive. The drawing is considered to be positive. So we are having in total 10 and 8, 18 active power requirement, and reactive power requirement is only 7.5 minus 6 or 6 minus 7.5, whatever, and it's going to be minus 1.5. Okay, so this is going to be the kVA complex power, okay, as is mentioned here. Moving on to the last problem, that is 8th in this session. A 3-phase cable is supplying 800 kilowatt and 600 kVAr to an inductive load. Okay, so 800 kilowatt, okay, it's drawn there, and 600 kVAr is the inductive load requirement of that is being transported by the cable. It is intended to supply an additional resistive load of the 100 kilowatt. Okay, so more the requirement has gone up, and we have an active power requirement of 100. So in total 900. Okay, so that's also shown in the diagram. Okay, without increasing the heat dissipation. What does it mean? Heat dissipation is caused by current. Okay, because resistance remains the same, it is only the current. So the current has to remain the same. The voltage is also the same, or in other words, the kVA, not kVAr, but VA has to be remain the same. Okay, so what is the VA? VA will be given by 800 square plus 600 square root. They take its square root. Okay, and now what is asked is, by without increasing the heat dissipation in the cable, by providing a 3-phase bank of capacitors connected in star across the load. Okay, given the line voltage is 3.3 kV, 50 Hertz, the capacitance per phase of the bank expressed in microfarads. So it's a more involved question, but there's no harm at all. Okay, why? Because we have already drawn, and we understand that now without heat dissipation, you have to go from you have to take the active load of 900 kilowatt, but you have to go a little. You have to supply the reactive power using the capacitor bank such that the cable does not contain the cable does not carry more current. Okay, so how do we go there? We have already calculated kVA. That is to be maintained constant, or else you can do it at one go by saying that you are having 800 square plus 600 square minus 900 square. Okay, and then take its square root, and so it becomes 436. The earlier requirement was 600 kVAr. Now we have to supply a little from the capacitor bank, and then bring it down to 436 kVAr as the reactive power requirement. Okay, so now what do? We have the capacitors to do that, and these capacitors are connected in star across the load. Okay, so each one of them has to supply the required kVAr. How much is required? 600 minus 436, which is going to be 164. Okay, so this 164 has to be now shared by all the 3 legs of the capacitor bank. So how much is that? That's equal to 54.67 kVAr. Remember, it's all kVAr. Okay, so far we have been talking about kilo. Okay, now we move on to how do we find out the reactive component. Okay, reactance of the capacitor bank of each of these capacitor legs, and then we move on to the capacitor. Okay, so how do you get Xc? The same thing, voltage square divided by kVAr will give you, or VAR will give you the reactance. Just like kV square divided by R gives you the power, or kV square by X gives you the reactive power, kV square by reactive power gives you Xc. So Xc is the same as equal to, so now everything has been transported to the kilo part has been removed. So 3300 into 3300, which is the line to line voltage. So divided by root 3 divided by root 3. So 3300 into 3300 divided by root 3 divided by the kVAr considered in terms of VAR. var, which is the same as equal to 54,670. Okay, so it tells us that the ohmic value of the reactance is equal to 66.4. Okay, so now 66.4 can be divided by, this is equal to 1 by omega c. So so when you set 1 by omega c as equal to 66.4, and omega we understand is equal to 314 because it's a 50 hertz system, easily the capacitance value can be calculated as equal to 47.96 mega farad. Okay, so this is a very easy problem, but there are two steps to it. First and foremost, we must understand that since the cable has to retain the cable must not be overheated. And the voltage is constant, the current has to be maintained constant. Okay, so you don't go for active power or reactive power. You just think in terms of the apparent power. Okay, so apparent power tells us that you have to maintain 800 square plus 600 square root of that, that's equal to 1000. Okay, so 1000 kVA has to be 1000 kVA has to be maintained. Okay, so 1000 kVA, if you deduct from it 900, of course vectorially, or 1000 square minus 900 square, then take the square root, you will see that you have that the machine still whatever the power still takes 436 kVR, and the difference between the two, that is earlier it was having 600 kVR, now it is 436 kVR, so the difference between them has to be now borne by the capacitor bank. Okay, and each of these legs will take 1/3 of the total, so we are having 54,670 vars as being the allocated the var that each of these capacitors need to produce for reducing the burden on the load. Okay, so we see that. So now we are having we are going to the next phase, wherein we see that the reactance of each of these legs can be calculated by per phase voltage, which is the 3300 by root 3. Okay, square it. So we are having 3300 into 3300 by 3. Okay, and then divide by the var, not the kVR, because we have taken 3300. So you get what is called as the reactance. Okay, so reactance is 66.4 ohms, and which is equal to 1 by omega c. Omega is equal to 314. Simply calculate. Okay, so here you will need the calculator. Okay, so that's all that is there here. I think all through I have tried to make the distinction between active power and reactive power, and how we can. Okay, there are more problems of this genre further, so we'll be able to do them as well. Yeah, so and then of course the distortion factor is an important introduction that has been made. More of it should be covered in the power electronics domain, but still we have talked about the converter. So we have talked about two aspects of a converter. One is of course the fact that the true power factor is given by the power factor as taken from the fundamental multiplied by the distortion factor, and the distortion factor is given by the fundamental RMS divided by the total RMS, which includes the fundamental as well also. Okay, so we did the problem accordingly, and then we also saw that active power can be computed purely based on the voltage, the current, and the power factor only. We don't need any other additional information as was done in the second problem. Okay. Thirdly, when we are talking about the admittance diagram, please convert everything into admittance, because then it's easier to draw them, because you can see what is happening in each of these parallel paths to which contribute to admittance. And when you have a zero admittance, it means infinite impedance, so it definitely passes the current, so we have what is called as admittance. Okay, because of the other circuit. Okay, so far I suppose it's okay for you, and we will move to the last of the sessions soon enough. Thank you.